I am most proud to introduce Dr. Linda Kay. She has an education. She got her PhD from Harvard,
Yeah.
fellow alum. Glad to have her here. It's glad we can speak secret Harvard language after this. But no, she has a PhD from Harvard. She's the professor of Earth and Planetary Sciences at University of Tennessee. She's been there since 2006. She's the Kenneth G. Walker Professor, and she has many, many other awards. And she has numerous peer-reviewed publications that can be viewed at EPS. There's the, I guess that's her CV link. Wish my slides would quit moving on me. But without further ado, I'm going to introduce Dr. Kay. She's going to talk about deciphering clues to habitability, the Jezero crater on Mars. And I'm going to stop sharing here, and I'm going to turn this over.
Okay. Well, I thank you, Don, for that extended introduction. And, you know, if there really is secret Harvard speak, it's been so bloody long, I don't remember it.
It's secret.
I'm pretty much a Tennessean by now. So I'm very honored to be able to talk to you all today. I've talked for the Kentucky Paleo Society and stuff, you know, several times in the past, many years ago now, about the work that I've spent most of my career doing, which is looking at ancient carbonate rocks and looking at stromatolites and interpreting environments of the early Earth. But about a decade and a half ago, I started on a new pathway. And it was sort of funny because I was just coming home from field work in West Africa, and I got a phone call from somebody who said, "You want to go to Mars?" And at that point, I had told my husband that once I had this last field season, we would settle down and have a family and stuff like that. And so, you know, I get this phone call, "Do you want to go to Mars?" And I think my first answer was, "Who are you? And you do know that I know nothing about Mars." But it was a scientist who builds cameras for Mars missions and for other planetary missions. And he had heard enough about me, and he said, "We don't need you to know anything about Mars. We need you to be a good geologist." And that sort of brought me into the world of Mars. My son, who I got pregnant soon after, my son has just turned 17 last week. And so it's now been quite some time that I've sort of split my life between carbonate rocks of the ancient Earth and the rocks of Mars. So today we're going to sort of combine that and say, well, what can we learn about life and habitability and the potential for life on Mars? But this is the Darwin Day lecture, so we're going to start with our good old friend Charlie. If I can figure out how to put all of those pictures of people someplace where I can't see them. And Charles Darwin actually spent a lot of time actually thinking about the ancient Earth and thinking about how life actually originated on Earth. And in a letter to a botanist, Joseph Hooker, he actually said, "It is often said that all the conditions for the first production of a living organism are now present, which could ever have been present. But if, and oh, what a big if, we could conceive of some warm little pond with all sorts of ammonia and phosphoric salts, light, heat, electricity, etc. present, that a protein compound was chemically formed and ready to undergo still more complex changes." So in this quote, he's actually given our science, it's given the geosciences a huge step forward into the study of astrobiology. You know, where could life have developed? How did it develop on Earth? Where could it have developed on other planets? And this idea of a warm little pond in which organisms first arise can sort of remind us of places like the Grand Prismatic Hot Springs in Yellowstone. You know, here we see a warm little pond. We have geothermal energy, we have water, we have nutrients coming in from the land and from the water percolating through the rocks and picking up chemical nutrients. And we see in these this broad array of colors, partitioning of environments that are different largely in terms of temperature, and carry very distinct microbial inhabitants. So we can go from this and say, okay, we have a warm little pond on Earth. Could we have had warm little ponds elsewhere? And we begin to ask the question about whether or not the Earth is alone. Now, the Earth is probably not alone, but we don't really know what that means. We have to define all of our different parts. So here we have a picture of our Earth, the blue marble with our beautiful clouded atmosphere and the huge oceans we have and the green land masses. But remember, this is not how it always looked. And if we go back to something like the Murchison meteorite, which was found in Australia back in 1969, so I was 2 years old at the time, when we look at the Murchison meteorite, we actually find that it contains a huge array of amino acids. Amino acids are often thought of as the building blocks of life. These are what make up our RNA, our DNA. And so these amino acids are really important. And with the finding of amino acids in a meteorite, at the same time that Miller and Urey were experimenting in the lab and making amino acids by having fluids and an atmosphere and a charge of electricity, it's suggested that, in fact, those building blocks of life are really widespread in our universe. And if we start to think about Earth and Mars, which is going to be our focus for today, the basic building blocks of these two planets are much the same. So here we have an artist's depiction of what our solar system would have looked like before the planets formed, when we had a protoplanetary disk. We would have had a proto-sun in the middle, a really hot region around that would be hot enough that you wouldn't even be able to condense metals from that. And then as we move outward from the center, we see partitioning of this planetary disk by temperature. When we hit this first dotted line that I mark as the soot line, this is where organic materials can simply condense from the gases that are within this planetary disk. And so we can start getting organic components. And then when we move out further and it gets colder, we get what's known as the frost line. And this is where we start to see ices in early solar systems. This might be water ice, might be carbon dioxide ice, might be methane ice. But when we actually think about now putting our planets and sort of wiping up all of this dust with the accretion of the planets, Mercury would have been inside of the soot line. And so we probably don't have much of an organic contribution to Mercury. Venus was probably quite near the soot line, and Earth and Mars were outside of the soot line. So anything outside of the soot line would have been accreting organic molecules. But we're still inside of the frost line. Outside of the frost line is where we started to build our gas giants. And so in terms of where in the universe the Earth and Mars formed, they should be quite similar. And so we can think about this lovely, slightly manipulated image from National Geographic as a representation of the commonalities between Earth and Mars. We have two planets. They're rocky terrestrial planets. They both have and had active volcanism. That volcanism would have put volatile gases into the atmosphere. And I manipulated this picture a little bit further to put a comet coming into the atmosphere as well, to demonstrate that both of these planets would have also had a cometary contribution of ice to help build up a water and a volatile inventory for the planet. And so there's a lot of reason why we should expect the Earth and Mars to be quite similar. But there's something very different about Earth and Mars too, and it's worth thinking about this in terms of habitability. So here we have to scale Earth and Mars. Mars has a diameter that's only 46% that of the Earth. It is quite a smaller planet. The thing is, that's actually important when we start thinking about habitability and the ability to sustain a habitable environment on a planetary surface. For one thing, Mars has a lot less gravity. And that means ultimately that the planet Mars is incapable of having as thick of an atmosphere as Earth does. And in fact, the atmosphere of Mars right now is only about a tenth of that of Earth in terms of partial pressure. But not all of that is gravity. Mars should, in fact, have a thicker atmosphere than it does. The other part is the cooling of planets. During accretion, there's a lot of frictional and radioactive heating, and we accrete and melt these large masses, which become our planets, but then they have a cooling history. Mars is smaller, it cooled much more extensively. Mars has a much thicker crust than the Earth, and it does not have any semblance of plate tectonics. The other thing is that Mars appears to have cooled enough to have lost its magnetic field. So our magnetic field, as most of us probably know, is formed by friction of within our core between the rotation of our liquid outer core and our inner solid core of the Earth. Mars doesn't have that. Mars does not have a global planetary magnetic field. And that actually matters because in this cartoon of the Earth, what we see is the sun pushing out all of this radiation, the solar wind. And we can actually see in the depiction of the Earth here how the Earth's magnetic field gets deformed. It gets deformed, but it is still there. And that's been so important for the Earth because it has actually kept the solar rays from actually stripping off our atmosphere and blowing it out into the outer solar system. Mars wasn't so lucky. Mars had most of its atmosphere blown away, probably about 3.8 billion years ago, which is when it looks like it lost its magnetic field. And so when we think about searching for life on Mars, what we're really doing is searching ancient Mars for habitability. So here we have an artist's rendition of Mars at a much earlier state where it might have had water still on the surface and where it had active rivers, where it had an atmosphere with clouds that could rain onto the surface of onto the surface of Mars. So with that introduction, let's actually go back to Darwin for a second. Because when we think of Charles Darwin, we think of this grand old man, the man who articulated life on Earth, the geology of the Earth, and how life has evolved through natural selection on Earth. But we have to understand that that was an older Charles Darwin that did that. And when he was a young man, he didn't have all of these grand thoughts yet. You know, the understanding wasn't there yet. And understanding in its infancy really is just observation. And so there were many years in there where Darwin was traveling the world and where he was simply observing the world around him and noting all of the similarities and all of the differences. And it took a long time to build the story for which he is famous. It's the same thing on Mars. We are really in our infancy. We are largely making observation. Our understanding sometimes is laughable. Sometimes we feel really good about ourselves, and sometimes we're like, I don't know what the hell's going on. But these observations are going to lead us to an understanding in the future. So when we move to Mars, we actually see in this map, this is a topographic map on Mars where blue are the low spots and reds are the high spots. And I've put on here the localities of all of our landers or rovers that have landed on the surface of Mars. I only came to Mars with the Curiosity rover, which landed in August 2012. So it landed over here, over on the right-hand side of the screen, in a place called Gale Crater. So if we take a look at Gale Crater, we begin to see why this was chosen for a landing site. Again, here we have a snapshot of a topographic profile of Mars. We have the highlands in the south with all of these reds and yellows, the northern lowlands and all these blues and purples. And we have this sharp division between the two. This is called the Martian dichotomy boundary. Now, we can for now, we're just going to ignore the fact that we don't actually know how this boundary formed. There are a number of different hypotheses, but when it comes right down to it, we don't know. But there's a big division between topographically high regions on the south and topographically low regions on the north. The other thing we see in this picture are all of these little wiggly channels all along the edges here, all the way up here. These are fluvial, so river channels that are cutting deep valleys. And as expected, because gravity still works, we see these deriving from the highlands and flowing towards the lowlands. And then we have Gale Crater. Gale Crater is about 110 kilometers wide, and it's really deep. We can see with even this white color here. It's a really deep hole. It's essentially a bathtub that's sitting right on that dichotomy boundary. And we can see that some of these channels break through its rim on the southern edge. That means for certain that any fluids that travel through these channels that cut through this rim would have ended up in this bathtub. And therefore, we probably had standing water. Water, was this our warm little pond? Perhaps it was. This shows a nicer picture of the northern part of Gale Crater. This was the landing ellipse, and we landed just a little bit east of the center point of that ellipse. And over the last decade or so, we have moved from our landing point, traveling along outside of this black patch of sand until we got to a clean spot. And then we've sort of wiggled our way up through this. And right now we are about right here. It doesn't look like very far, but it's actually tremendous. And we're heading towards this main channel that cuts through the upper parts of this central mound. But during this traverse over the last decade or so, we've actually learned a lot. One of our early signs that Gale Crater probably was a habitable environment was this image. This was in a place we called Kimberley. And, for all of us field geologists that haven't been in the field because of the pandemic for a couple of years, we'll take you to Mars as the next best thing. I mean, look at this beautiful geology. You can see these beautiful sort of 5 to 10 centimeter bedded strata, and you can see this continuing all the way down. We're actually closer to the crater rim. We're looking down into what would have been the deep part of the crater, and then we have the central mound back here. And then we can see that black sand, that patch of black sand that we could see in that previous image. If this were a little bit closer of an image, you would actually see that the top surface of this broken bed right here actually has wave ripples on it, which is wonderful. We're seeing sedimentary structures indicative of fluid action. And you can see sort of down here an unconformable surface where we have these dipping beds, and then we have some flat-lying beds on top of this. Well, what we're actually looking at here is a dissection of a deltaic cliniform. So we're actually seeing where a fluvial channel was flowing down the edge of the crater and flowing into a standing body of water and depositing deltaic deposits. And this tells us that someplace further out in the crater, we should find our evidence for our standing body of water. Well, in fact, we do. When we get out further, we find lacustrine sediments. These are very mud-rich sediments. They are very well laminated, as you can see with each of these lamina, the thickest ones being about 1 millimeter thick, a lot of these being sub-millimeter in thickness. So we see evidence of very fine-grained deposits making it through the river system into the lake and then settling out of the water column. But there's still a lot that we don't know. We don't know if this was a deep lake or a shallow lake, if it was a perennial lake or an ephemeral lake. And so we have to keep looking and building up our observations before we can get an understanding. Well, shallow or deep? I would suggest that it's actually probably pretty shallow, because in amongst these beautifully layered muds, we actually see channels. And so in this particular outcrop, we're looking at a segment that's about 50 centimeters wide. We see these beautiful bed forms. And so we had bed forms traveling down a little channel. And when you go in really close, high magnification to this stuff, it's actually pretty coarse. It's sort of millimeter. It's very gritty. It's quite, medium to coarse sand. And so I would guess that, in fact, this lake was never particularly deep. And perhaps at shallower times, we actually had these streams actually incising into it. Other places where we look at these mudstones and use our DRT, our dirt removal tool, which is essentially a wire brush that we spin and brush off the red dust that's ubiquitous across Mars, we see something very different when we look down at this bedding plane. We see that the sediment itself is very fine grained and quite reducing. It's quite bluey gray. And then we see all these beautiful little lathes. And to all of the geologists that are listening to this, you say, yeah, that looks like gypsum. And in fact, it does. These are beautiful little sort of centimeter long at their longest, couple millimeter wide lathes that look like gypsum, calcium sulfate, that you might find forming in the muds of a dried lake bed or a nearly dry lake bed. So to me, that this suggests that the lake was probably not perennial. It might have been ephemeral. Over what timescales? I don't know. So perhaps it was perennial over years or decades, or maybe even hundreds of years, but spent other times as an ephemeral lake. We don't have that time scale yet, but what we see is much like what we see on lakes on Earth, that they're quite variable through time. And then as you go up further in the stratigraphic column, I mean, the rocks only get more beautiful in Gale. Here we see beautiful sweeping crossbeds. These are fossil Aeolian dunes. So this is a lake edge deposit where we had big sand dunes that were just migrating across. And you can sit here and you can map out each of the lamina, and you can map out boundaries between different bed sets, and you can put together a story of the wind direction, the migration of these dunes. So ultimately, what we have in Gale and what we've seen over the last decade is a lacustrine to subaerial environment that we could imagine very well existing on Earth and being completely habitable. Okay, so let's move on to Jezero Crater and the Perseverance rover. So this is all the exciting stuff because we landed less than a year ago. So in about a week, we have our 1 year anniversary of being on the surface. Perseverance landed here, quite a ways from Curiosity, right at the edge of a big impact crater basin called Isidis Basin. But it is, again, right along the dichotomy boundary for pretty much the same reasons, that water flows from high spots to low spots. And here we have a crater, a hole right at that boundary, and perhaps it was a lake. But this is a very different mission than Curiosity, a really different mission, even though our rover is built along the same body plan. It has much of the same instrumentation, although more of it, as well as some experimental instrumentation. What makes the Perseverance rover mission different is it is a sample return mission. We have a drill on the end of the arm with some stabilizers that we can drill core that are about 1 centimeter in diameter and about 10 centimeters long. We seal these in titanium tubes, store them up underneath the belly of the rover, and then when we get to the end of our prime mission in about 2 years, we will take all of the samples that we've left and we will drop them in a cache. And then another fetch rover, another mission will come, lift them up off the surface, and then they will be returned back to Earth. So we should actually be getting our first samples, in situ collected samples from Mars, in about 2033. I retire in 2033, so I'll never see these. But this is an important mission. We have to build the context. We're looking not only for evidence that the environment might have been habitable, but we're looking for lithologies that will help us understand the parameters of habitability and understand whether or not any evidence of life is actually preserved in the rocks. So they've given us some help. We have, along with our Perseverance rover here in this nice little GIF, we have our Ingenuity helicopter. Ingenuity has now flown almost 4 kilometers in terms of flights, and has flown in 19 different flights. It's still going strong. Some of us sort of wish it would die so we can stop flying it and pay attention to the rover itself. But the thing is, Ingenuity has given us a very different look because it can actually fly above the surface. It usually flies about 5 to 8 meters over the surface, and it has multiple cameras on board. And so we can actually fly at places that the rover can't get to and get some imaging from that. So why Jezero? Well, why Jezero is very much the reason why Gale. As I said, it's at the dichotomy boundary. This is an artist's conception of Jezero crater, but what we know is that there's a channel that breaks through the crater rim on the western side, and then there's an outflow channel over on the eastern side. And if you look at the elevation of the inflow and outflow channel and say, well, in order to make that outflow channel, water had to be at least that deep, it suggests that at times there was a lake as deep as 150 meters deep in Jezero crater. When we actually look at our landing site, we can sort of start to see the diversity of what Jezero crater looks like today. Over here on the left-hand side, we have the crater rim with this large channel that comes through it. We see a beautiful deltaic deposit with this big meteorite crater in the middle of it. But there's so much we don't know yet about Jezero. We know that Jezero crater is shallower than it should be. There's actually a very well-known relationship between the diameter of a crater and its depth. It's much shallower than it should be. And so that tells us that there's probably up to 1 kilometer of material in the crater that is beneath what we see as the floor of the crater. So we don't know what the older stuff is in the crater. The oldest material we see in the crater are in these lobate inliers. Here marked Seta. We see another one up here, and it's a pale-toned, highly fractured rock. Sitting on top of that is this dark-toned unit that retains a lot of craters. We simply call this the dark-toned or the crater floor. There are some hills further out into the crater that we wonder whether or not they're remnants of the delta, or maybe they're fine-grained sediments that represent lake deposits that have otherwise largely been eroded from this area. And then we see some other interesting mounds here that I'll show you pictures of in a couple of minutes. The other reason we like Jezero is we can use spectral signatures from orbiting satellites to say something about mineral compositions. And so this is a particular color stretch that highlights different mafic minerals. And so what we see is that along the crater margins, there's actually a lot of olivine, and there's also spectral signatures for carbonate and silica. We see that as well in the oldest material in these inliers, that it should be dominated by olivine, but also has spectral signatures of carbonates. The delta itself spectrally has a lot of low calcium pyroxene, and then this dark toned floor has a spectral signature of high calcium pyroxene. Now, none of this tells us that that's the whole rock, because the different spectral bands are sensitive to different minerals. And we could be looking at 80% olivine, or we could be looking at 3% olivine and then have the other minerals blind to us. We don't know, but we do know that there is this diversity. And diversity of mineralogy can lead to diversity of chemical reactions, which can lead to potential diversity in metabolic reactions, thus life. So I have put a little yellow dot here is where we landed. If we go to our landing site, now I have little white dots on this floor that shows our daily drives. We actually spent a lot of time in the last year. We spent 100 days, 100 sols, Martian days, right here near the landing site. And it's because it took nearly 100 sols for us to get our equipment tested and working. So we had to commission all of our equipment. We had to unload the helicopter. We had to get the helicopter moving on its first flights, etc. So while we were there at our landing site, we were taking images. We were taking images over here towards the delta, over here towards the delta remnants, over here towards this older material, Sita, which is Navajo for amidst the sands. You can see all of the sand dunes in here. And we're deciding what to do once we got moving. Well, what we decided is that if we traveled south, we called this inlier the thumb of the mitten, that if we traveled south along this inlier, would actually give us our best opportunity to image and to understand the relationships between the Sita materials and the crater floor materials. We also spent a lot of time looking at the delta remnants, because if these were really fine grained lacustrine deposits, those might be very favorable for retaining organic signatures, might be something we really would want to collect and bring home. And we ultimately decided that the drive was too far out there. And so we drove down here along a ridge that we called our 2B Ridge. We popped into Sita, sampled. The blue dot is where we are right now. We're actually on our way back. And then we're going to drive around this mitten and make a beeline for the delta. Now, you might say, why are we going all the way around instead of right across here? Because rovers don't like sand. And it would actually take us much longer time-wise to travel this direction towards the delta than going all the way around this. Right now, we think that once we get up back to our landing space, if we shut up and drive, we can get around this in probably about 1 month. It would take us about 2 months to travel across all of the sand and rocky elements here. So what have we seen? Well, we're going to start first and show some pictures of the delta, because this is what's coming up and has enticed us so much. So this is the picture of Kodiak Butte, one of these isolated buttes along the delta, and it is astounding. It is absolutely astounding. This could be anywhere on Earth. We see these darker rocks of the crater floor in front of us, and this mound in the back with these beautiful sandstones with beautiful sedimentary structures. If we actually look more closely on this, we have to keep in mind that this picture, the distance of this butte from the rover at the time of this picture is about 2.5 kilometers away that we're looking at this. So we can use a camera on our mast that gives us our highest resolution images. And this may look a little bit fuzzy, but again, we're realizing we're looking at individual laminae within this butte from 2.5 kilometers away. And we see these beautiful flat-lying lamina at the bottom, these beautiful cliniforms, and then flat-lying beds on top. This is classic sedimentology. Bottom set beds, cliniforms, top set beds of a delta. And here we're actually looking at it. And then if we look a little bit over to the left, we see a little bit further down, and we actually see these large cliniforms. But then look right here where my cursor's circling. We actually have a second progradational set of cliniforms coming down at a different angle on top of that. And then we probably have a third up here. We're actually seeing evidence in this rock 2.5 kilometers away for dynamic rise and fall of lake level during the time that the delta was being built. And if we go back to that initial artist's conception of Jezero as this big lake that might have been 150 meters deep, even the very top of our delta is only about 40 meters above the current crater floor. And so we think that upper limit of 150 meters was probably a catastrophic event, and most of the time the lake was smaller. When we look at the top of the delta escarpment, we see this again, some beautiful lamina. This is again about 2.6 kilometers away. But here we see a region where we have big boulders, and this large boulder, and you can see the shadow, that this isn't just a figment of our imagination with the shadow, it's actually protruding from the outcrop along the delta escarpment. That's about 2 meters in diameter. So that's the size of a Volkswagen Beetle. These are not just a gravel deposit. This is a boulder deposit. And in order to get a boulder deposit way off, right near the edge of a delta escarpment, we're no longer in a deltaic environment. We're probably at much lower water levels, if any water, and we're probably looking at catastrophic flood deposits that are being overlain over the top of the delta. So we can start putting together this incredibly dynamic view of this watery environment. So once we saw that, we got excited. We wrote our first paper for the mission, but then we had to get on the move. So we decided to go south towards that thumb and travel along what we called our Tooby Ridge. And these were some rocks that separate the crater floor, and these are crater floor materials, that dark toned, from the inlayers of older material, which would be off to our right in this image. And, they're beautiful outcrops. I mean, we get fabulous images, but it starts to remind you that even as a geologist, how much can you tell from a rock from this different distance? Well, what we can say is this bottom part is more friable and falls apart, and the top part is more massive. But it's actually been a huge challenge to try to understand what these rocks are. They appear broadly layered, but Jezero is a very dusty place right now. We can barely take an image without having a dust devil. There's been a lot of aeolian abrasion that turns rocks into ventifacts and polishes them by the wind and makes them very difficult to understand. So here's actually a rock along our Tooby Ridge, and we can see over here at the right, this glinty polished surface. And you can see a roughness and you say, okay, maybe this is granular in some way, but it's hard to tell. And then over on the upper left, we can see these grooves. That's all aeolian abrasion that has just sculpted the top surface of this rock. And then we can see this really reddish material. All over these rocks, we have an iron oxide coating that just sort of plasters on the outside of these rocks, making it impossible to see what's underneath. And so we had to take the next step, which is to use an abrasion tool and to abrade a spot into it. And so what we do is abrade a spot. This is about 5 centimeters wide, and it's just short of a centimeter deep into the rock. And then we have a poof, our GDRT, our gas dirt removal tool. We have compressed gas, and we go poof, and we blow the sediment that we've abraded off to the side. And then that gives us something that we can look at. Well, this abrasion, the Bellegarde abrasion, has been fascinating. We can take images of it at various resolution with our various cameras. And the best image we have of this is from a black and white camera only, but it's called our ACI camera. It takes a picture of this small area. It's about 1 by 2 centimeters. And this is what it looks like. And so in the next couple of pictures, we're going to sneak in up close on this abrasion patch and see what we see. Well, the first thing that we see is a lot of textural variation. So here I have close-ups of the ACI image at the top in black and white, and then we've colorized them using a color image. And so we see all sorts of things. We see quite a few crystals that appear to have facets on them, so they look like intact crystals. We see things that even look like skeletal crystals, which would be crystals that grew very rapidly. We see other bits that, particularly with the color, look like they might be rounded clasps containing a bunch of crystals, but the staining around the edge is alteration of iron oxides. So it suggests that this is actually a transported clast. So what are we looking at here? The answer is we don't know. Many of us have decided it's probably pyroclastic. but we don't really know. But what we do know is in other places of that patch, we see things like this. I'm a carbonate sedimentologist, and so this absolutely thrills me. What we actually have here in this big white bit is a patch of gypsum, so calcium sulfate. Around that, we see this sort of uniform gray stripe that is equal thickness. It's isopachus, and we see it coming around here. And we see it actually around some of these faceted crystals, but it goes completely around that gypsum. That gypsum is a late stage void fill. The earlier stage is an isopachus cement of some sort. We don't know what its mineralogy is, but we actually see a number of these voids. Here's another one down here. Here's another one down here. About 40% of this rock appears to be void space. And so we have evidence of a rock matrix, which we don't really understand. Some of these beautiful faceted crystals, which I actually wonder whether or not they are actually crystalline material that's growing into a void, because we actually see this isopachus cement rim coating it on all sides, which suggests that it's sticking up in 3 dimensions into a void, and we're coating it. So these might be crystals. Think of them as think of this as a tiny geode with crystals growing in, and then being filled by later fluids and other mineral precipitates. So we're seeing evidence of a lot of water interaction, and that's exciting. We don't know. Really, with a couple of pictures, it's really hard to tell what we're looking at. And we have sedimentologists like me who think that we see sediments, and igneous petrologists who say it's all igneous. And it's so difficult to actually come to an understanding with just these pictures, but we're bringing home a sample. So this is actually an image of our drill bit extended with a drill with a core inside of it. These are the stabilizers that hold the drill stable on the rock. And then we turn this and look into it. And here's our sample. The sample has now been sealed in a titanium tube and is just waiting to come home. And we will actually be able to use all of our high resolution instruments to determine what the rock is in the first place, what fluids were there, what was the evolution of the fluids as these voids got filled. So then we move on and we move to the older material, to the Sita material. And this is what it looks like. These are sort of 50 centimeter steps, this beautiful stepped outcrop, broadly layers. It appears to fracture along smooth layers. It looks with the weathering like there's layers in between. Even in these pieces of float, we can see some layers. We see some finer, more obvious layers down here. Beautiful rock. And some of us looked at this from this position and said, something that's clearly sedimentary, yay! And then we took pictures of it. So again, with the remote microscopic imager, the one that we were able to take those long distance photos of, this is of a photo of a rock that's only about 8 meters from us, but it gives us wonderful resolution. And we can begin to see all of the individual grains that make up this rock. Here are some close-ups of some chunks of that. But what's really interesting here is, first, if we look at the top of the rock, we don't see anywhere any evidence of any grain size change near these things that look like bedding planes. And in fact, on a lot of them, we're probably seeing extra erosion by wind, because you can actually see individual grains that have simply been eroded in half, cleanly in half, by erosion and wind erosion. So we can look in total at these grains. We don't seem to see any grading, any preferential grading or grain size. Each of these grains, I've actually measured hundreds of them at this point, are about between 1.4 and 1.8 millimeters diameter. So they're a good sand size grains, but we look at them and they're very angular. And they're very smooth. They don't actually show a lot of weathering texture, which makes you wonder whether or not there might actually be monocrystalline. And then we have sort of rims around them sometimes, and then we have some intervening material between the grains that we can't really identify. So once again, we grind into this. This is another one of these abrasion spots, but I sort of cut it off because I want you to see the rock outside of it. Because if you look over at the right, you can again see these sort of 1.5 mm size angular grains in different colors of gray. You also see this red iron oxide coating that covers so much of our rocks. And then you see what happens when we actually grind it. You see a lot of radial features in here. That's actually from the grinding mechanism. So you have to sort of learn how to look through that. But we see these paler colored individual grains. I don't know what that triangle is. Don't ask me. And then we see darker sort of greenish gray grains. We've looked at this stuff with a variety of different instruments, and one of our instruments, Pixel, actually goes down and does a little X-ray analysis of different spots. So this is a pixel color stack. It's a ratio of a green wavelength and an infrared wavelength of just a small portion of that abrade spot. You can see sort of over to the far right-hand side is the edge of the abrade spot. But this sort of highlights those crystals better without all of those chatter marks. And we can see that many of our minerals appear to be the same material. These would actually be those paler minerals that are in the pale blue. And then the darker greener minerals are actually what's seen here in very pale blue. And so Pixel has actually been really exciting with this spot. It's a delicate instrument. It's been a little bit troublesome, but what it ultimately gave us was this. Now, to highlight, this is going to be a small area right about here where we have this darker blue grain that seems to be indented into this paler blue grain. So that's what we're seeing right in the middle. Each of these little boxes is a little X-ray scan. And so we get a little X-ray diffraction curve for each of these spots. And then what it's colored as is right here, we're looking at an iron calcium map. And so what we see is that all of the light tone grains, so our primary grains that we see in this rock, are very iron rich. And in fact, they are an iron rich olivine. Okay, they are monocrystalline olivine crystals. And what this blue is a calcium pyroxene. And for anybody who spends a lot of time looking down a microscope, all of a sudden, this no longer looks like a granular bed that had angular sedimentary grains that were transported. This looks like an igneous rock. And this not only looks like an igneous rock, but when you start measuring the size of the crystals, it doesn't look like a normal igneous rock. It looks like a cumulate deposit. So a cumulate is, imagine if you have a lava lake or a very thick lava flow where you start crystallizing olivine, but the flow is still very molten and very fluid. And so you start settling, just like you would a sedimentary grain in water, you start settling those olivine grains to the bottom. And in doing that, you actually settle certain grain sizes, and so you get a grain size distribution that in many ways mimics a sedimentary grain size distribution. But then the material between these grains is simply crystallized material that crystallizes as the molten material cools completely. And one of the other phases that typically fills in the intervening spaces are pyroxenes. So this looks like an igneous cumulate deposit. This is not what we expected to see. So ultimately, what have we learned? In the past year, it has been a wild ride. We've learned that, particularly from our images of Kodiak Butte, here circled in yellow, we've learned that Jezro's Western Delta shows a much more dynamic sedimentary environment than we envisioned from analysis pre-landing. The well-layered materials of the crater floor are still a curiosity. We don't really know what they are. We don't really know their means of emplacement, but we do know from the abrade patch that there's a lot of evidence for aqueous alteration. And so this may have been laid down prior to the lake and been interacting with overlying lake waters. And then from the Sita materials, these things have just surprised the hell out of us. And they're dominated by monocrystalline angular olivine crystals that look like an igneous cumulate deposit, that perhaps the base, this crater actually had a lava lake in it that solidified, eroded, then had this blue material, the pyroxene-rich material of the crater floor laid on top of it in layers. And we have a lot of evidence that there are layers there. And then at some time later, we flooded the whole thing. And then we started building out this delta into it. So we actually have this really complex history that our observations are putting together. Now, is this a habitable environment? Oh, absolutely. And all of the things that we had hoped are still true. We know we have a wide variety of mineral diversity. These minerals look like they have interacted with water, and we've precipitated other minerals directly from those fluids, filling those voids. And then we also have this sedimentary delta that we haven't yet reached, so we don't really know what it looks like yet. So we clearly have a habitable environment. And so we are just working our damnedest to keep building this context and keep sampling things that will come home in a decade that will be able to fill out the story. So where to next? We head to the delta. Right about where I've circled on the delta with that yellow circle, here's an image from satellite view. And this is astounding. I mean, I can't wait to get here. We don't have a lot of topography, but where you do, we have gray, dusty surfaces, but we also have these white areas, pale areas that are dust-free. And we can see here channel deposits after sedimentary channel deposits after channel deposits and channel deposits. We're seeing in this one image from space the potential of this delta having distributary channels moving over the surface through time during the building of sample. And we're going to be able to drive through this and see what those materials look like up close. I can't wait. And then we have an area that we've been calling the triple junction. This is right up near the main channel where the main channel of the delta, which is right up here, comes in from the crater rim. And we see in this picture just an astounding array of materials. We see really blocky material that looks really crumbly and blocky up top. We can see all the shadows of the blocks. This is actually what caps the delta, and it may be those gravelly deposits that we're seeing right along the delta escarpment. We also have these beautiful layered deposits underneath that, which is what I showed you in the previous image. These are actually probably finer grained materials, sedimentary materials from the channel deposits. And here, they're actually sitting on top of some of the material that from space appears to be olivine carbonate and really richly carbonate bearing material. So is this the same cumulate deposit that we're seeing elsewhere? Is this actually a crater margin, perhaps spring deposit with carbonate? We don't know what this is yet, but once we get up here, we're going to have all of these within, 100 meters of each other. So we're going to be able to look at all of those. And then ultimately, we're going to exit off to the west of this picture and drop our cache near the crater rim. So with that, what we've seen is that, we do have good indications from two different places now that Mars had habitable environments. But what we're also seeing, particularly in this newest mission, is we are not at the stage of Darwin understanding evolution by natural selection. We are at the state of making observations. We need to put this together piece by piece into the puzzle. And there are a lot of new puzzles as we get a closer look. So with that, I'd like to say thank you, and I'd happily take any questions.
Excellent presentation, Dr. K. Thank you so much. We have, I have one question here. I only had one come in on the chat.
Well, people can ask them in person.
Yeah, and it's from John Pop. And John, you may want to ask it yourself, or I could ask it for you. It's whatever you'd like to do. But he had a question about the when you showed the earlier the slides with the aeolian deposits, is that there were some striking fractures looked like through them. He was wondering, is that tectonically influenced?
That's actually a really good question. I had a PhD student finish a couple years ago who actually worked on some of the fractures in Gale Crater, and it appears that most of the through-going fractures that we see are probably hydrofractures. And so what she started to do is to really map out the behavior of, because the fractures she was working on are actually infilled with gypsum and different calcium sulfate, and sometimes an older layer of something of unknown mineralogy. But she was really looking at the structure of the mineral fill within the fractures, as well as the behavior of the fractures as they move through rocks of different lithology. Because with hydrofractures, you're looking at overpressuring of subsurface fluids, and that overpressuring is causing them to move and to fracture overlying materials. But we don't know a lot about the mechanical and material behavior of rocks on Mars. And so one of the ways of doing that is by tracing the behavior of fractures. And so she did that, and then we started working with a woman over in our mechanical engineering department here at UT in modeling the fractures. And so we only got so far with Rachel's dissertation. She's actually now a systems engineer over at JPL and is actually interviewing next week for a position where she might be put in charge of the whole Mars sample return process, which is incredible. But I have a brand new graduate student at UT who used to work for Delta Airlines as an engineer. So her background is engineering and astrophysics, and she's coming in and is going to do some detailed finite element modeling of fracture behavior, because sometimes we see the fractures come up and then move sideways, rotate as they hit a certain lithology. Other times they enter but then arrest in that lithology. And all of this is telling us about relative pressures and material properties that we're going to try to constrain through the finite element modeling. Now, once you get into some of the aeolian stuff, and once we start moving up the central mound of Gale Crater, there have been some things that have to be tectonic fracturing. They are local, though, but what we have are we've been going through a thick stack of aeolian materials that are really soft. And I think as erosion has happened, we're seeing stretching and pulling apart of the outcrop. And so it's local fracturing, but it's not a large scale tectonic fracturing, but there very clearly seem to be some joint patterns that suggest we're looking at a tectonic stress field of some sort. Anything else?
Are there any good Earth analogs to what you're seeing on this? Like a freshwater or a briny water lake on the igneous
yes,
rocks?
Yes, I mean there clearly are, and most of my life I've spent looking at Precambrian carbonates and evaporite deposits in the Precambrian, but they've mostly been marine. I'm working with a student up at Purdue University who I won't malign him. He knows, I think, who knows diddly crap about sedimentology, but a lot about spectral observation of rocks. And so he actually visited Lake Salda in Turkey as a place that has spectral signatures of olivine and carbonate. So Lake Salda is an alkaline evaporative lake that sits on top of an ophiolite. So it's sitting on top of ultramafic materials, and it's precipitating carbonates, largely magnesium carbonate, and a hydrated magnesite and stuff like that. And so it's a very different mineralogy, but he collected samples when he's down there, and he actually just spent a week on my microscope and on the SEM actually looking at textures. The only things that have been written about Lake Salda are from the mineralized microbialites, these actual beautiful stromatolitic mounds. But when you actually look at shoreline sediments, it's much harder to say that the mineralization had anything to do with the biology, and that you're probably looking at a strong climatic signal. And so he is looking at that lake in terms of spectral signatures, and then asking questions about to what extent might these spectral signatures that we see of olivine and carbonate, what likelihood might they have of giving us biosignatures when we get there.
Has the helicopter been much aid in like scouting sites, or is it just experimental?
It's largely experimental. I mean, it's a test case, but it's real sexy, so everybody likes it. Its cameras are good, but they're not our highest resolution cameras. And quite frankly, there's just so much data that comes in on an early mission that half the time I don't even know what mission I'm on. I mean, I work a couple days a week in Jezero Crater, a day a week in Gale Crater. I teach 3 days a week, so right now, Monday, Wednesday, Friday, I'm teaching Stud Strat first thing in the morning and an astrobiology course last thing in the afternoon, and fitting all of this stuff in between. And you can tell, none of us ever expected to have 2 working rovers at the same time. And we move from one rover to the other, and we can barely keep our language straight. We're calling instruments the wrong things. There's so much data that trying to keep up with it is almost impossible. You pick your battles and you keep up with what you can.
Had a question come in on the chat from Michael McGlue. He doesn't have microphone access right now, but he wanted me to ask you this. He first of all, he complimented you and said, "Wonderful talk, Dr. K. Do you think subsequent Mars missions might focus on interdeltaic environments of the crater lake? I wonder if perhaps more carbonate buildups could be found in these environments."
That's why the olivine carbonate units that we see in Jezero, it's really sort of interesting, because we see it in these inliers where we first visited, where it appears to be an igneous cumulate, but we see the strongest carbonate signatures right along the crater edge. And so you can imagine that you have a crater, and so you have these highlands of the crater rim, and you're going to get spring deposits, and we actually know that most of the Martian crust is very mafic, and in fact outside of the crater just to the west there's actually some strong olivine signatures, so there might be a broader cumulate deposit. And so you can imagine that if we have rainfall that is seeping through all of this olivine rich material, it's altering all of that olivines, and it's and serpentinizing material, and what you're going to get is carbonate, and you're going to build up carbonate in your water. And you could envision, even if you've been someplace like the Great Salt Lake, of having springs flowing through the hills surrounding that lake, and then coming into the lake and bringing a chemistry that you could precipitate microbial mounds. So the richness of carbonate along the crater edge is intriguing, because it is in a position where we would expect groundwaters to perhaps exit as streams. And then all of a sudden you start thinking travertine, and you start thinking microbial buildups. And I don't know what we're going to see when we get there, and we're going to have to, but we're just going to have to wait. The problem is that Mars is just still damn hard. It is, we actually drove the other day 246 meters in a day, and that was record breaking for Mars. 246 meters. It was huge. And then of course we faulted out, and it took us 3 days to drive the next 4 meters. This is not an easy thing to do. These rovers are incredible engineering, unbelievably, incredible engineering, but they're on the edges of our tolerances. And so we tend to fault things out, and we can't always do things, so sometimes you want to think, and you're like, if you could put a man there, give a man air and let him hike, 6 kilometers, you could learn more on that 6-kilometer hike from a geologist walking it than you're going to learn from a rover. But ultimately, we can't really get man there. And so the rovers are what we have. So I know that didn't quite answer your question. I don't know where we're going. I don't know when because our next time back on Mars is quite simply going to be to pick up these materials. And after that, I don't know when we'll even go back to Mars. Right now, the sites are being set on missions to Jovian moons and some of the ice moons of Jupiter and Saturn.
Excellent. Are there any other questions? Anyone else, if I can interact with Dr. K?
Okay, well, if not, I want to thank. It looks like we ended up with a really good crowd here today. So thank you so much.
Excellent. Doctor, we really thank you for joining us all the way from Rocky Top. And just thank you so much. The chat is just blowing up with people. Excellent job. What a fascinating talk. One said that, the YouTube videos and other things are really good, but these photos with explanations are unbeatable. And you speak our language, and it's just a fascinating talk, and I can't thank you enough.
Well, thank you for inviting me. I've talked to some of the Kentucky groups about Precambrian stromatolites. Now I've talked about Mars. So, you'll have to have me back in 4 or 5 years when I've decided to do something else.
Absolutely. Well, I want to thank everyone from the Kentucky section for joining us tonight. I hope everyone can take something with them. And Dr. K, we thank you from the bottom of our hearts, and we appreciate you sharing your research. And wow, this just opened up a whole new world to me as far as what's really out there and what you all are actually looking at. So I can't thank you enough. And if there's no further questions, then we will wrap it up right here. And thank you everyone for joining us, and we look forward to seeing you next time.
Great. Thank you so much, everyone.
Yeah. Donald, could you make sure that we get a link if you post this on YouTube or someplace?
Absolutely, buddy.